Okay, so today we're going to talk about exponentials and logarithmic functions, and specifically exponential and logarithmic functions with the natural base e. Okay, so natural base e, it is something that occurs in nature. If you are familiar with the compound interest formula, you will see that this formula looks very similar to that compound interest formula. As we make n go to infinity, so as we make n get bigger and bigger, the number that this approaches will be e. Okay, so we're taking the limit as n goes toward infinity, and this is in fact the number that it trends toward. So that's what e is. It is not a variable, it is its own number. Also a button on your calculator that you can find in a couple different places that will give you that value and allow you to use that as a base. Okay, so let's talk about continuous growth. Here is your basic function for continuous growth. Okay, so we're going to have P, which is going to be our starting amount. It is growing continuously at some rate R. Okay, and then T is our time in years. So if we have those things, we can find out what the amount is at the end of a specified period of time. So let's look at an example of that. Now remember, our formula is A equals E to the RT. So our principal, our beginning amount is 5,000. E is our base. Our rate is 3.25%, which we are going to need to put into decimal form. Just because it has a decimal in it does not mean it's in decimal form. We need the decimal equivalent of the percentage, and then we multiply that by 5. And let's see what that is. So at the end of 5 years, we should have $5,882.24. Okay, and we get that just by plugging that all into our calculator. Okay, I want you to pause the video and try this one. So make sure that you're entering all these things in the proper places. Principal, your rate, your time, and see if you get the same answer. Sorry, times 3. And we should have gotten 22. $549.94. Remember to round appropriately. All right. The other thing we're going to do is look at logarithms, and specifically natural log, okay, which is ln, natural log, lnx, or it is the same as log base e. So what we're saying when we say lnx is the log base of e. Okay, now remember, and I always think about logs like this. Logs are the opposite of exponentials. So if I have 2 cubed, I know that answer is 8. Okay, so if I were to take the log base 2 of 8 equals 3. The question that a logarithm is asking is, if I have this base, which you'll notice matches my base over here in the exponential, what exponent do I need to raise it up to get out an 8 for this specific example? So the answer to a log is the exponent. And there are some properties of natural logs. If I have the natural log of two things that are being multiplied together, then that would be the same as taking those two things apart and adding them. Let me give you an example of that. If I had the natural log of 6, that is the same as the natural log of 2 plus the natural log of 3, because 2 times 3, right, this is the natural log of 2 times 3. 6 is 2 times 3. Okay, so that's how we would break that apart. Okay, now we're not going to just randomly pick numbers to break it apart. We're going to use this when it makes sense to use it. If I have the natural log of a fraction, that is the same as the natural log of the numerator minus the natural log of the denominator. Okay, the natural log of something raised to a power is the power times the natural log of that thing. And let's look at that one for just a minute. So if I have a natural log of, let's say, 81. Okay, well, I know that 81 is 3 to the 4th power. Okay, well, that means that it's the natural log of 3 plus the natural log of 3 plus the natural log of 3 plus the natural log of 3. Okay, so I have 1, 2, 3, 4 natural logs of 3. So that's why that property works. Okay, and remember, for property number 4 here, we're saying, and I'm going to switch this to log form just to make it a little clearer. Log base e, remember that's what ln is. Log base e of e equals 1. Okay, what can I raise something to get out itself? And the answer to that is always going to be 1. Okay, what can I raise something to and get out itself? What exponent would I raise it to get out itself? The answer to that one is 1. Okay, the natural log of 1 is 0. And this works no matter what your base is. So we can even do a different base. And actually, let's think of it this way. 8 to what power equals 0? I'm sorry, equals 1. 8 to what power equals 1? Well, anything to the 0 power. So 8 to the 0 power is 1. Okay, e to the 0 power is 1. Right, so this is saying e to what power would give me an answer of 1. So your answer is always going to be 0. Okay, this is something called the change of base formula. So this is useful when you have a calculator that does not do logarithms. If you look at the buttons on your calculator, there should be a button that says log on it. That is log base 10. And then right below it, on most calculators, is an LN button. This is true if you're looking at the TI-84 for sure. And LN we know is log base E. So those are the two bases that most calculators are able to calculate. Now, on the 84s, we should be able to calculate any base, and there's a special way to get to that, and I can talk you through that a little later. But if we have a calculator that does not do this, so if you have a TI-83 and not an 84, you need to know this formula. Okay, so if I have log base 6 of 8, Well, my calculator doesn't know log base 6. My calculator knows log base 10 or natural log. So I can change it, and it doesn't matter which one I do. I can do natural log of 8 over natural log of 6. That will get me the answer. Or I can do log of 8 over log of 6. Try both of those. We should get the same answer. Which is 1.16. Okay, and then this last property. E with the power of the natural log of x is x. E and the natural log cancel each other out. They are inverse functions. So the same would be true if we had a natural log and we wanted to solve that, we would use an e. If we have an e and we want to solve that, we would take the natural log. So they are inverse functions. So we can use those both ways. Okay, a few things. We've talked about domain before, but we did not talk about it with natural log. So natural log. And let's think about this. If I have a positive base, so let's say we'll just take an easy one, 2. What power, question mark, remember the answer to a log is an exponent. This would be the answer to a log. Tell me which power I'm going to raise 2 up to, where I'm going to get out a negative number. Okay, now remember, we have to take 2 and multiply it by itself. So 2 times 2 times 2 times 2. When is that ever going to be a negative of any kind? Well, the answer is it's not. So we don't have natural logs for negative numbers. Domain of a natural log is 0 to infinity. Okay, the range is all real numbers, but the domain is 0 to infinity. Okay, so let's find the domain of this one. I have to keep this 0 or bigger. And actually, I should say bigger than 0. So I want, let's cross that out. I want 5 minus 2x to be greater than 0. I can't take the natural log of something that is 0 or less. So the first thing we're going to do is subtract 5 from both sides. So I have negative 2x is greater than negative 5. Now I'm going to divide by negative 2. Remember, this is an inequality symbol. So when I divide by that negative, it flips the inequality sign. So I have that x has to be less than 5 halves. So x is some number less than 5 halves. That is your domain. You could also write that as negative infinity to 5 halves. And there would be parentheses on both sides of that. Okay, let's try this again. So this time I want 7 minus 3x to be greater than 0. Subtract 7. So we have negative 3x is greater than 7. Divide by negative 3. Again, when I divide by negative 3, I have to switch that sign. So I get that x is less than 7/3. And then that's your answer in interval notation. All right, let's use these properties to solve exponentials. So the first thing we want to make sure we do is have our exponential isolated on one side. Okay, so in this one, the thing raised to the exponent is isolated. We said the opposite of e is natural log. So what we're going to do is apply a natural log on both sides. So I have natural log e to the 3x equals the natural log of 2. Okay, we're not worried about the natural log of 2. Our calculator will find that for us. On this side, it has the effect of canceling each other out and bringing down that 3x. So we have 3x equals the natural log of 2. I still need to get x by itself, so we still have to divide that by 3. So x equals, let's go ahead and see what that is. So we have natural log of 2 divided by 3. So we should get that x is 0.231. All right, on part B, this time our exponential isn't isolated. This piece is your exponential. We need to divide that 250 off both sides before we can start. I cannot apply a natural log to both sides until I divide that off. So we're going to divide both sides by 250. So we're going to have e, the 0.015 t equals, looks like 3. Now I can take the natural log of both sides. So I have natural log of e to the 0.015 t equals natural log of 3. So that means 0.015 t equals the natural log of 3. And finally, we're going to divide both sides. So we're going to get t equals natural log of 3 divided by 0.015. And we get 73.24. Okay, doubling time. Doubling time. So if I know the doubling time, I can find the rate. All I do is take the natural log of 2, divide by the doubling time, and it gives me my rate. If I know the rate, then I take natural log of 2 and divide it by the rate, and that will give me the amount of time it takes for something to double. So you will want to write down these formulas. Okay, so here we want to find the growth rate. Okay, and we know the doubling time is 6 months. So ln2 divided by 6 months, and that will give us 0.116 or 11.6% per month. Okay, we divided it, and our period of time was months. So our rate is 11.6% per month. Now, if you thought of 6 months, well, we can put this in here, 7.6. If you thought of 6 months as half a year, so instead you went this route, let's look how that goes. So we had natural log of 2. Instead, we divided it by 0.5 because it was half a year. You would have gotten 1.386, which is 130. 138.6% a year. If you multiply what we got above by 12, since that is a monthly rate, then you would have gotten to this 138.6% per year. So it's the same thing. You just have to make sure that you are defining the period of time that you're looking at. So you could have gone monthly or you could go yearly. You just have to state which way you were doing it. Okay, and lastly, let's go ahead and solve a natural log function. So we have this function, 5 plus 7 natural log x plus 3 equals 19. Let's subtract 5 from both sides. So we get 7 natural log x plus 3 equals 14. Okay, I have to get the natural log isolated before I can exponentiate, which is use that base of e. So I want to divide that 7 off of both sides. I'm going to have natural log x plus 3 equals 2. Okay, now we're going to exponentiate. We're going to use a base of e on both sides. So on the left side, we have x plus 3. And on the right side, we have e squared. And finally, we're going to subtract 3 from both sides. So we get e squared minus 3. Now, that is an exact answer. Some of you I know will want to change that into a decimal. That's okay. Hopefully you leave it as its exact answer. But if you need to put it in its decimal form, that's okay. All right, so that was it for our natural base